Okay, in this lecture set, what we're going to learn is a very convenient non-dimensionalized equation for Mn. And so the first question might be, why would we have to change that equation we already did? Why do we have to take the dimensions out? So for example, you might say, is 5 square inches a lot of steel to put in a beam? Well, it depends. It depends on how big the beam is. And so the actual amount of steel doesn't really tell me anything unless I know the size of the beam. So that's an example. And let me show you what I mean on the iPad. Okay. Share that. Okay, so for example, what I'm saying, you're asking me is 5 square inches a lot? I don't know, 5 out of what? And so, for example, this problem that we had, this 4 number 10 bars was 5.08 square inches. And so what would give me a good idea if that's a lot or not is to get the ratio of the area of the steel to the area of the concrete, okay? However, what we're going to find out pretty quickly is that what's more relevant to us than the area of the concrete is the area of the concrete only up to the middle of the steel. Okay, so instead of B times H in the denominator, we're going to use B times D, where D is the concrete only to the middle of the steel. The concrete below the middle of the steel, we're not going to worry about. So if I do that, I get 5.08 divided by 20 times 27.5. Okay, so this number will tell me if it's a lot of steel or not. Or at least it'll tell me, maybe not you. That's 0.0092. And I just happen to know for 4 KSI concrete and 60 KSI steel, 1% is a reasonable amount of steel. So that's a reasonable amount of steel. And to be honest, how I picked the 4 number 10 bars for this problem, I made this up, was I took 1% of B times D. And I knew that would come out okay. Okay, so what we're going to do is take the equation we derived last time and take out all the dimensions. We're going to turn like AS into AS over BD and MN. We're going to non-dimensionalize that as much as we can. Okay, so before we do that, I thought it would be a good review to calculate MN for this beam. This is from homework 2. And in homework 2, we got the allowable moment using working stress design was 250 foot kips. Let's see what MN is for this beam. Okay, so I'm gonna turn myself off and just continue. Okay, so MN, so remember T is just FYAS, so 5.08 times 60. That is 304.8 kips. T equals C, solve for A. So remember C is 0.85 F prime C B times A, and that'll equal T, which is FYAS. Okay, so that's T in the numerator. So 0.85, 4, and the width was 20. Okay, so A is 4.48 inches. Z equals D minus A over 2, 27.5. 25.26 inches. And finally, MN is T times Z. So 304.8 times 25.3 inches. 25.3 times 304.8. That's 7,700 kip inch. 642 kip feet. 642 kip feet. So phi mn, the reliable amount of moment, is 0.9 mn. 577 foot kips. So 577 foot kips is phi mn, and the m from using working stress design was 250. So it's over twice as strong as what that allowable moment was with the unfactored loads. And so let's say your unfactored loads go all the way up to 250. Strength-wise, your safety factor is 2.3. So your beam is 2.3 times as strong as the maximum moment you would ever have on it. Okay, so that's a quick review. And what we just did was you're given F prime C, Fy, the cross section, and AS. You need to find Mn. Okay, so we did T equals C. Okay, so here you go. Here's the strains. You turn those into stresses, and especially remember this weird Whitney stress block, and we know this is yielded. And then we'll get C times T, C equals T, and this internal moment arm we call Z. Okay, so we use T equals C to solve for A. We did that last time. We did Z was D minus A over 2. And then finally, we had Mn equals T times Z. So there's T, Z. And we derived this equation last time. And it's very useful. It's something you can put in your calculator or Excel. But we're going to non-dimensionalize that. You're going to do this a lot. And so you want to be able to do this quickly and accurately. So we're going to make an equation, and it's not as clear, right? Because if you look at this, you can sort of see like, oh, that I remember that's T. This is sort of like C. Oops, pause too long. I guess it changes it to a circle. C, and oh, there's T times Z. I mean, you can sort of see it if you remember the derivation, but what we're about to do will make that all go away. It's hard to understand, but it's very convenient. So it won't be as clear, but it'll be quicker. And this equation we're about to derive is only for rectangular cross sections. And you still need to be able to do this basic concept for non-rectangular sections. Okay, so here's the derivation. And I guess you could just, this is just algebra. You could skip it if you want. The first thing we're going to do, we're going to take that D and factor it out. Okay, so there you go. Now see there's a BD in there. Okay, AS, remember rho is AS over BD. So that means AS equals rho BD. Okay, so that's this right here. Okay, and then that makes these cancel right here. So we're getting good. Oh, and then what we did was we took this BD here. Oh, and here's AS BD. Okay, and here was AS, which is rho BD. So you end up with this. And what we're going to do, we're going to take this and put it on the other side. Okay, so you have this. Okay, so you get Rn equals this. Now, this equation here is very, very handy. I have this equation in my calculator. I use this equation a lot. and it is very handy, especially when we do design. I'm gonna talk